Hey, I'm going to record the second part of this video, and I want to record it on the roof, so you can check this out. The view is great, kind of, but of course we are going to talk about the neural networks. So now we're going to implement the backpropagation path, and this is going to be the difficult, most difficult part of all. So let's actually do this. Hola. Yeah, it's Spanish. I know my Spanish is good, so let me get into here. Okay, so now we're going to start. I'll put in the description the start of the video. All right. So as you know, we ended here where we defined our forward pass. Let me clear this out. Now we're going to implement the backward pass, and we'll start with the loss. So I'll say loss is equal. We are going to use mean squared error. So we're going to take a mean first, NP mean. It's already inside the NP, or you can use actually mean, but I'm not sure. Like, it's not gonna work, I think. Yeah, there is no such. So np.mean, and then what we are going to check here out is that what's our squared error and what's our error at all. So our error is ypred minus y, and then I'm going to square it because we are talking about the squared mean squared error, yeah. And this is the reason why I will square it. So now the question here is, why is this error? Because you see, logically, if you have 7 apples, and your friend comes to you and say, well, you have 5, the error here is 7 minus 5, which is equal to 2. All right, so I think that's pretty much easy to understand. And then when we say squared, it means that we will just square it and we will get 4. So this is just a technique already, so it's actually incorrect for this example that his error is 4, but it's pretty much good for the gradient descent and the derivative itself, so when it's kind of high. So yeah, and then we take a mean because of the a lot of samples inside. We have 12 samples there, like 12 letters and 11 letters and 1 space, but we can call them all characters. So now we get our loss, so let's print, we'll say f, and then loss is equal to curly brackets loss. Okay, so let's check this out. What's our loss? And it says 0.17, 0.17, 0.17, etc. Yeah, so this is kind of how it is. Now we know our loss. So in order to make a backpropagation, first we need to calculate the derivative of the loss. So the derivative of the loss is simply how much shall we change how much should we change loss to kind of decrease our error, okay? So and then we'll calculate with respect to our loss, so how to decrease an error to each parameter. And if you're not familiar with this, I'll switch here, and as you can see, here is the derivatives topic, then points not visualized. And if you'll check out all of them, you will get into it like particularly, and you will understand the whole concept of it. Here is the whole math behind it, like under the hood. So yeah. Now let's calculate the derivative. So we'll say derivative of loss is equal to, first, the derivative of loss is going to be ypred minus y, and just multiply by 2, because the derivative of this is just the power rule. So if you're not familiar with the power rule, again, I've explained it somewhere here. So multiplied by I think I've explained it in the chain rule. So this is going to be where's the chain rule? Oh yeah, it's here. But anyways, not the main topic today. So y pred minus y just y, yeah, and then we'll divide it by the length of our samples, which is this just number of samples. The reason why we don't multiply it because is that like obviously it's not the part of the not the part of the back propagation, so or not the part of the derivative, so this is obviously so. Now, the second part which we need to calculate is a sigmoid function. The derivative of the sigmoid function, again, we've put it already here, is derivative. We just need to set it on true. So we'll calculate derivative of y pred, and it's going to be equal sigmoid. Then inside sigmoid, we're going to define our, obviously our y pred, yeah, so we're going to define y pred in the sigmoid, and then is derivative we're going to set into to true. So now this is pretty much well done. Let's calculate the first derivative of the weight, or the change the weight which we need to do. So basically the derivative of weight with respect to loss is going to be, let's dive into it, but first let's calculate the derivative of weight, and then I'll show what is the derivative of weights with respect to loss. Now the derivative of weight is going to be just simply z2. So I'm going to say a derivative of weight 3 is going to be simply z2, yeah. So obviously because we multiply them and then it becomes well, it's partial derivative, so we don't have a need in it. So z2. So now interesting, what is it? So what's the shape of it? As you can see, the shape of it, y pred minus y, is going to remain the same, and it's going to be 1/12, just simply because of it. Because we're doing some operations here, but we don't change the shape explicitly. So now I'm interesting also what is the shape of the dy pred, and the shape of it is going to be just obviously the same shape, because we've just applied the sigmoid function. Okay, so now this is we are already forming the chain rule, because when we say the derivative of the weight with respect to loss, it means that it's going to take all the chain rules inside. So we will take dy pred inside of it and also multiply it by this. So now in order to do this, we're interested in the shape 1.112, and then z2. What is the z2 shape? It's 120. So if it's 120, I think I'm interested in let me think about it. So we have our weight 3 is the 20 and 12. It means we need to form the shape 20 and 12. In order to do this, we're going to transpose this and then multiply it by the this value. So in order just to do this, you just multiply d loss first on dy pred. So I'll just copy this, and then I'll transpose this and use np.product, np.product, then comma here supposedly, and so now I have my derivative of the weight tree. In order to check if we are going in the right direction, we'll just now let me make it for the bias as well. So for the bias is going to be the same, but we're not going to use z2 because of the partial derivative. So the partial derivative of the bias here is just simply 1, because we are taking the power rule and it becomes 1 because everything in the power of 0 is simply 1. So now we can update it already and check this out. If we are decreasing our loss, if we're going into the right direction, we are going to continue make a back propagation. So in order to do this, I'm going to say that w3 minus equal to, this is basically this. So w3 multiplied by the learning rate, which is multiplied by the w3, okay? And this is b3, and then b3, and the same thing applies. And this is how it works, okay? Wait, I did wrong this a bit. It shall be so. Okay, so we just first we do multiplication, then subtraction. Okay, put it back. So, but in order to do it easier, what we can do is just simply say minus equal. So it's gonna be just easier and more convenient. So yeah, I don't wanna like write a bunch of code, like a needed bunch of code. Now let's, yeah, we've updated our weight, so we can say updating. And now let's make a forward pass again. So I'll not be too like, I'll just copy it, okay, copy paste, just for the sake of checking if our loss decreases. Because we've changed our weights. Yeah, of course we changed our only first pair of weights and biases, but to check if the loss decreases and we get an error, the reason is because, of course, I just copy paste, which is not correct. So here shall be B3 because shape is not equal. And if I'll get into it, as you can see, we have first loss 0.178 and second 1.77. It means that we are decreasing. If we're decreasing, we're going in the right direction. So it means that we can continue to update our weight. So now the next thing, I'm going to update the weight too. So in order to do this, again, we will calculate the derivative first of the weight 2. So the derivative of weight 2 is just simply, now let me check this out. It's just simply a1. Yeah, partial derivative, of course. And then we need to check, we need to take, yeah, I think I will mess you in this moment. So let's again check this out. So we're calculating the derivative of the loss. Then using the chain rule, we're calculating the derivative of y pred because it was applied before this function. Okay, before this. Then after y pred, we've calculated the derivative of this. And this was correct. So now we're continuing our chain rule for the W2 from here. Okay, so in order to get into W2, first I need to find the derivative of the sigmoid function, because I can't just go in the Z2 and take the partial derivative of weight 2, second weight, because I need first to calculate the derivative of it. So to calculate the derivative of it, to calculate the derivative of it, I need to check, I need to just take it as A2 and then say that sigmoid is going to receive A2 and is D just simply going to be true. Okay, so now this, let's actually just make it so to don't mess everything up. So this is for our first updating. Okay, so this is our next step. So now I'm about to calculate the weight 2. So I'll say the derivative of weight 2 is going to be equal first dA2 because it follows the chain rule. Then the partial derivative of weight 2 is just simply A1. Okay. First we need to calculate the shapes. So we have 112, 112. Then for dA2 we have 120. As you can see here, 120 shape. It means that one will get 112, as we did here. We just multiplied it, where we'll be not able to get the correct shape, because if we will just cast it, it will result 1220 shape. But as you can see, here is no 1220 shape. Yeah, so in order to accomplish our mission, we just need to transpose this to get just one-on-one metrics here. In order to do this, we will first take d loss. Then d loss we will multiply. First we'll transpose it. It means that we'll change is going to be 1 multiplied by 112, which is dy pred, d underscore y underscore pred. Okay. So now we got shape 1 to 1. So shape 1 on 1, I want to multiply by the shape of 1 on 20. In order to do this, I'll just multiply it by dA2. So it's going to result a good result. And then I'll just shall I use dot product here? Like, obviously, I just need to multiply them. Let me check this out. So just take A2. No. A1, of course. So I've been mistaken. Yeah, I did a mistake here. I said to you that we're going to multiply it by a2, but we actually need to multiply by a1 because this is actually our partial derivative of it. So let's check if we get the correct shape. So the correct shape is going to be just 120. Yeah, of course, shape. No, we got a mistake here because we are trying to... Okay, so it is saying that I'm trying to... Yeah, I transposed it, and then... What is wrong here? Let me check this out. So it says 12 by 12. And I can't really understand why. So this is 1 by 12. Then I'm interested in this shape. This is basically 1 by 12. And what I've been doing is transposing this in order to get the correct shape. So if I'll transpose it, oh yeah, so of course, yeah, I need just transpose the second one. So instead of transposing this, I'll go here and transpose U. So, and check this out again if the shape works out okay. So now we get another mistake here. Again, it says 12 by 12. Yeah, I need to change U, I think, guys. dy pred. So what is going on? I just checked it out right now. So it says d loss. We need to multiply by the dy pred transpose, and then we will get... Oh, of course. Yeah, here's the error. I'm using just simple multiplication, but it's incorrect. So in order to... Yeah, so now I get my error, got my mistake here. So my mistake is that I need to transpose it, and I need to do it inside the np dot. So there's the difference between them. I'm just going to say comma, and then here. So I think this will work out okay. Now check out this shape again. Hopefully it will work. It will work fine. Okay, so now we got 120. And this is exactly shape what we was about to find. So now in order to find the bias, it just actually bias just multiplying by 1, but I don't write it or code it here because it makes no sense. Like it's this calculation wouldn't need it. Like so this will be the bias, and everything works fine here. So now we'll update these weights. So we will say our dw2 will be here, and then db2, and then we'll just change them out. Now if we did everything correctly, and I always will encourage you to do so, I will make again forward pass, but then I comment this and check if there is a difference between them. If there is a difference, like if with these lines of code we're getting loss even lower than with just this, it means that we did the right backpropagation and derivative calculations. So you'll just get into it right now. Let me just show it to you. So now I run this, and I got 1769, and before, remember, I got 177. Remember this. So now if I'll comment this and run this again, I get 177. It means that we've even decreased our loss using this. It means that our like chain rule is still correct. So we're going fine. Now the last step is the calculate the last weights and biases, and we'll be done with this video. I think not more than, well, let's just do this. So in order to calculate it, first we need to calculate the sigmoid function, derivative of it. So we will say derivative of a1 is going to be equal sigmoid. Inside it I'll put a1, and then I'll say that is d is simply true, because I'm interested in the derivative here, and the derivative. Now we need to make again the whole chain rule, and then take the partial derivative of w1, which is just simply x. Okay. let's do this. So I'll say derivative of weight 1, and then we will calculate it. So let's start with this. Now, if we have shape 1, 12, 1, 12, it will not work out. Will it work or won't it work? I'm interested in the shape of 1 on 20, okay? If I'm interested in the shape of it, 120, when I'll just multiply it by this, which is 112, I'll get exactly what I want, 12 by 20. It means that this we can a bit optimize. So now I'm going to copy this. No, let's not optimize it at first, but I'll show you how to, why do we need to optimize it? Because I just need to copy this, and then at the end, like I need to take all of that, say npm dot product, and here I'm going to say like x, okay? So now if we got here 120 and this is 12 by 20, it's going to result as will it work out? Wait. No, it's not. It will not, because I'm interested in the shape of 20 of 20, and then 20 of 20 multiplied by the 12 and 20 is going to result exactly what I want. Yeah, I think so, because this is 12 by 20. So in order to achieve this, I think we will not create the delta. Let me then just delete this a bit. So here we have 1 multiplied by 1 on 20, okay? And then, oh no, still it will work out. So yeah, I think we'll add delta. Let me show you just what is the delta. So if I'll say here delta 2 is equal to npm dot this line, and then we'll use it, it's pretty much simple, right? So like it seems to be that this is awesome. It looks awesome, like we don't copy paste just 2 lines. So, and now I can use this delta 2 here, because this is the chain rule, this is how we follow it. And what I need to do is just simply multiply it. So what's the shape of the delta 2? The shape of it is 120, as I do believe. Yeah, 120. So we just need to transpose the derivative of weight a1, that transpose, and find the, of course, dot product of it, not just multiplication, because we're going to get the same error, I think. We can check it and then continue. So print dw1 shape, and we need to now get 20 by 20, and we got 1 by 1. And this is because I think I need to, yeah, of course. Yeah, obviously, now what I did is I casted 120 on 21. It resulted me 1 and 1. Now I changed them, and now it is 21, 1 by 20. So now it's going to be 2020. So yeah, I was interested in this. And the last thing is, again, we create np dot. Then we will pass the parameter here, which is going to be just x, the partial derivative of weight 1. So now we're going to get the shape 12 on 20. And we got a mistake because oh yeah, so obviously, yeah, we don't need this line of code, so just multiply them. So if we will multiply them, then we will get the good result, right? 120, and then simply transpose an x, okay? So if I'll transpose the x, I got 1220, and the reason is because when I've been doing dot product, I got 2020 shape, but when I used x, it means that the shape of x is just simply, where's the x? It's 1 on 12. So in order to get the right shape, I've been needing just 1 on 20. Now, yeah, hope this is helpful. So, and here for the b1 is just simply delta multiplied by a1. So as you can see, the delta is very useful, and this is the reason why we've created this variable to make a chain rule. Good. Looks good. Yeah. So now let's create a forward pass, and now let's check if all the steps just decreasing our error. So I'm interested in it. So yeah, just last line of code I forgot is make the updating. So I'm not gonna copy paste it, because this is good when you just write a code and you kind of memorize everything what you do. So you just say w1 minus equal to learning rate multiplied by the derivative of weight 1, and then the same thing we're going to apply to b1, which is just simply learning rate multiplied by the delta. Oh no, by the of course derivative of b1, not just delta, because delta multiplied here by dA1. So okay, it seems to be pretty much good. Now let's make other tests. So let me put it into here. No, actually it will be much more useful if I'll use multi-comments. So when I used three update, like 3 weights and biases, updating three weights and biases, I got this result. So what result will be if I'll just apply update two of them. So I'm going to just simply comment this. So I got this result, and as you can see, it a bit different. And then when we just update our one set of parameters, or one pair, which is the last one, we're going to get something like this. I'm going to comment this as well and leave just this. We got this result. So now we need to a bit look at does it work okay, and is it what we need to get, what we want to get. So let's explore this. So when I had one weight and biases updated, set of weights and biases updated, I got 177. Okay, so then when there were two, I got 176. It means that we've decreased. Wait a bit. So okay, so the third is kind of higher than the second, right? So we got 1, 7, 9, 6, 9, and 7. It means that this one is higher, and this is strange. This is literally strange. So now we need to understand what we did incorrectly at all. Like, let's put it back, and now check what might be incorrectly here. So because I can't really understand what's the problem here. So multiply by a1. Yeah, this is correct one. So probably the question here is that probably because the parameters there are high, they weren't be able to, they weren't be able to learn. So probably we need to make 10 epochs and then compare all of them. In order to do this, all of that we're going to place into the for loop. I'm going to just click tab, okay, and then I'm going to say for epoch in range of epochs, and then here. So what is the epochs? We're going to get here and say that our epochs is just simply 10 epochs, okay? Then I'm going to print my loss here, and then check if epoch divides by the epochs divided by 10 is equal to 0, and then I'm going to put this into this. Yeah, you will get into the sense of it a bit later. And then I'm going to print the epochs. Epochs, it's kind of iterations right now because we don't have much epochs here. And I'm going to just put this because it will work out okay. So we don't need to change explicitly all of them every time. So now when we get 10 of them, I'm interested again in the results, okay? So first we'll check the results with just one set of weights and biases updated. And we got something like this, and I'm wondering why is it in the different, probably yeah, I think here shall be just simply epoch, which is over 10. Wait, is it? Like, we're going to print epoch. Yeah, okay. So, and then our loss is going to be equal to, wait, like we're dividing epochs by 10. Now let's not make it at first. I'll just check if it. Well, let's delete it for now, because I can't understand why it works in such a way. Let me just emphasize that the loss shall be no more than 8 values, 8f, okay? And then I'm going to run this again. Why do we get lost 2 times here? Oh, okay, because I forgot to delete this one. So now, okay, now it makes sense. Then let's run again. Okay, so on the 9th epoch, let's actually +1 because it's always going to be like this. Okay, so on the 10 epoch, we got this result. And as you can see, we are decreasing. So with one set of biases and weights we updated, we got this kind of loss. Then let's check what is going to be resulted with 2 of them updated, 2 sets updated, and then we'll update. Oh no, I forgot to comment this. Let's check again the result. So the result became this. Now let me copy just the whole line. So okay, this is the result. Then what will happen if we will update the second set and the first? We got this result. This is fine. And then what is going to be with the third one? What is it going to result to us? Let me copy this and let's now check this out if it works. All right, yeah, so now it makes sense. When we have been updating just one set, we got 171 for the 10 epochs. Then for this we got 1648, and then for this 1647. So before the increasing happened because probably in the last in the first set there was a high values for our sigmoid function, so it just resulted in increasing, but at the end it's going to be decreasing, of course. So now we're slightly getting into it. So now I'm going to increase the amount of epochs. Let's say I'm going to have 100 epochs. And what I'm going to do is now implement this again because I've been stumbling because of the second forward pass in this range. So yeah, I'm going to check if epoch divided by the epochs over 10 is equal to 0. Then put it into it, of course colon here, and then here epoch plus this. Okay, so let's check if it works as I'm expecting it to be. No, it doesn't. The reason is because I divided actually by 100 by 10 is just simply epoch by 10, and so on. So why is it wrong? Like so my epoch is 1, 2, 3, 4, 5, 6, and so on. Then epochs divided by 10 is going to result 10. Oh yeah, of course, because I'm using not the correct one, so I need to use this sign. So now to check this out, yeah, it works okay. The last thing is that I want to be at integer without the dot O at the end. Okay, so now it works fine. Okay, we're decreasing, so we before we had 0.17, then we have 0.02. This is pretty much good, and I'm glad about our learning. So now what if I'll increase the number of it? Okay, so on the 1000 epoch we got pretty much good result. What about if there will be 10,000? And this is not that much actually, guys. So we got this result. So what was our previous result when we used 100 and 1000 iterations here? So the result was this, okay? So this was our result, and yeah, it's lower than R, because here's the here's the 4 zeros, and here's the 5 zeros before it. So it means that it's going to be better if I'll make also 100 epochs here. Let's check. Yeah. Let's just check what will it result to. And as you can see, we got even better result than for this file, probably because we've used learning rate here, because in this file I didn't use this technique, but this is a good technique, you guys. So now when we got our predictions, I want to print our predictions. So let's print y pred, and then no, let's actually do it this way, for I and j in our zip. As you can see, yeah, I'm in the darkness already. Yeah, kind of. But anyways, let's continue. A bit cold here, guys. So I'm going to zip first our ypred, and I can just say like this before you remember from the first part that we need to cast it to list. Okay, and then we're about to take the 0th element. Oh no, we can just say squeeze. Yeah, actually we can say squeeze. Before I used it, but squeeze, then initialize, and then that again. Okay, so we've converted it into list. Yeah, just believe me that it works out okay. Or you can ask ChatGPT why is it so, and then we will put y here. So then I'll say for print my let's say like this, 0.6 f, just 6 numbers after it, and then this as well. So and then we will use format to format it, and say let's actually change this for p, which is predicted, and for target, which is target, and then p, and then target. Okay, so let's check what will the result to us. So yeah, it goes. Okay, so as you can see, our predicted values almost the same as our target values. For one, it says that it is 0.99, which is almost the same thing. So here it says the same, like the same, not the same, but almost. And I think our neural network works pretty much well. So now in order, remember what I said before, that we did this because we need to then convert our data back. Now we have our normalized data, which is our ypred, so we need to convert it back to codes. So I'll say backed codes, and then our back codes is just norm, and then I'll take my ypred, then I'll squeeze my ypred, and then I'll convert it into the list. So in order to do this, just to list, and then I will use max code, or max normalized code, and then mean code, and then at the end is backed is going to be equal to true. So now I believe I need to get I'll get my outputs as an array. So this is going to be array of the yeah, you'll just check it out. So we train. It's actually better to use the Jupyter notebook, because it does not make it any time, like every time. We'll just get the result. So yeah, this is our result. Seems to be correct, everything, right? 107 because of LL. So let's check if our result is the same as the result with the codes. So I'm going just to copy this and check this out. Yeah, kind of like this. Oh yeah, we need to iterate it every time. Anyways, yeah, the mistake first here. We got a mistake here, and I am pretty much interested because why did we get a mistake there? So let's copy this and then put it at first, and run this again. So I'm interested, what did we get wrong here? So we had, and basically here is also wrong. And I think the reason is that we are forgot about the very, very important thing is to round it. So I want to round in my norm data the output, okay? So I want to first round it and then convert it into an integer. So I hope it will work fine. Let's check this out if it will work fine. Yeah, I hope so. Yeah, so as you can see, 72, 101, so you see it's almost, I mean, it's exactly the same. So the reason why we got an error is because integer just cast it down. It does not round it like from the fifth to the left and to the right. It just cast it down. So even if you have like 99 and you want to round it, you will not get 100, you'll get 0, like something like that. I hope this was helpful. So okay, so now I need to convert it into the string. So predicted string, okay, and predicted string is going to be equal to our vector codes. Just simply str code, put this array here, and then is vect just going to be equal to true. And I think now our neural network knows how to write hello world. And let's check this out. Hopefully our neural network can write hello world. Guys, this was nice. So actually right now it's ended, but a few things left to say to you. First thing is you can a bit design neural network in the another way. So you can change every 20 here in another number, but remember always about the dimensions and about the shapes. If you will change their, like the first layer you will do 25 for example, and the second 45, remember about the shapes. Probably you'll get an error somewhere here. So the best way is to just if you are not yet familiar with this, is to change all the 20th into the number you prefer to see. Like probably if you'll increase the number of the neurons, the neural network needs just 10,000 iterations to find the good results for our for our set. So if I'll of course make it bad, I'm going to get something like that, because the number of epochs is not that much good. Then I'm getting something better, and then if I'll increase this, I'm getting much more better. Then now it does not define the space, and then if I'll increase it more, I'll get a space. Okay, so you can explore it and a bit play around it. Also, what I wanted to do, so right now we've learned our neural network how to print hello world, but what if we will train it like on tremendous amount of text, like how ChatGPT trained? We're going to get a good model which can actually it can communicate with us, like kind of it can write some kind of text, right? So if we'll have tremendous amount of text, for example, in the next video we can train a neural network to recognize two phrases. Like if it sees something like random data, it can recognize the hello world and hello Max, for example. Okay, so we can distinguish it between it. Of course, for now it's just trained for hello world. So basically, our neural network, as we gave birth to our neural network, we kind of learned this baby to learn how to say hello world in the human recognizable language. And then in the next video we can of course increase the difficulty and complexity of the neural network. So this is it, 92 lines of code. Here is 93. Interesting. But anyways, this is how it works. You can play around it, and if you are willing to support my channel, you can always check the description. But of course, I don't require anything from you, so this is free, and you can use it. Like, you can do whatever with this. So have a good day, guys, and hope this was helpful.